We will now discuss section 5.2, where we will look at applications of exponential functions. We begin with an example for population growth. A biologist is culturing bacteria in a large petri dish. She begins with 1,000 bacteria and supplies sufficient food so that for the first 5 hours, the bacteria population grows exponentially, doubling every hour. We are first asked to find a function that models the population growth of this bacteria culture. We know that for exponential growth problems, we seek a function of the form p of t is equal to p sub 0 times a raised to the t power. This function tells us the size of the population, p of t, at time t. So I'm just going to make a few notes. P is the population. T is the time. P sub 0 is the initial population. It is what you start with. And the A is going to be a constant. We know in our problem that our initial population, it tells us she begins with 1,000 bacteria. So the 1,000 is our P sub 0. We also know that the population doubles every hour. So what does this mean? This tells us that after 1 hour, the population is what? We started with 1,000. We know that it doubles every hour. So we know after 1 hour, the population will be 2,000. So given that, this gives us a t-value, and it also gives us a p-value. So what I can do is I can take my general form for my formula. And my job is to plug in so that I can solve for A. So we know that the population is 2,000 when the time is equal to 1 hour. And so we can plug a 2,000 in for the P of t, and we can plug a 1 in for the t. We also know that the initial population is 1,000. So in for the P sub 0, I can plug 1,000. So this gives me a formula that looks like 2,000 is equal to 1,000 times A. And now I can solve for A. So I can divide both sides of the formula by 1,000 and come up with an A value of 2. So that is the first step in writing a formula, is to solve for that constant value A. So now, if we want our formula, we can come back and we can plug in P of t is equal to 1,000, and keep in mind the P of 0 in our formula is always going to be 1,000 for this problem because that is our beginning bacteria. So we can go ahead and plug that in. We know that the A value is 2, and it's raised to the t power. And so now we have a function that will give us population at any given time. Part B of the problem asks us to determine when the population reaches 16,000 bacteria. So they're giving us a population and they're asking us when. So they're asking us to find the t. So let's look at that. We have our formula. P of t is equal to 1,000 times 2 raised to the t power. And we want to know when, so we're looking for the t, does the population, the P of t, equal 16,000. And so we're going to plug in 16,000 for the P of t, and we're going to work at solving for the t. So we can divide both sides by 1,000. That's going to give me 16 is equal to 2 to the t power. Now remember how we solve exponential equations. We isolate the exponential, which is done. We then try to write both sides with the same base. So we have 2 to the t. So the 16 could be written as 2 to the 4th. And once it's written with the same base, we then set our exponents equal and solve if necessary. So we know that after 4 hours, the bacteria will equal 16,000. And so now we know that t is equal to 4 when the population is equal to 16,000. Part C asks us to calculate the population 2.5 hours after the scientist begins. So we want to find the population and we're given the time. So for part C, we know that 2.5 hours will be our time. We're going to substitute in 2.5, which is 2.5 as a decimal, into our formula. So again, our formula looks like P of t is equal to 1,000 times 2 raised to the t power. I'm going to plug a 2.5 in. For the t, and I'm going to solve for the population. Now, the easiest way to evaluate what is on the right-hand side is simply to use your calculator. And so we'll type in our calculator 1,000 times 2 raised to the 2.5 power, and we'll get approximately 5,657 bacteria. And so that completes our first example. Example 2, we'll look at an exponential decay problem. Determine the base a so that the function a of t is equal to a sub 0 times a to the t power accurately describes the decay of carbon-14 as a function of t years. To work this problem, we need to know that the half-life of carbon-14 is 5,728 years. This is a fact that could easily be looked up or researched. So I'm going to write that down to start, that we have a half-life for carbon-14, 5,728 years. Now, what that means is that if you started with, say, 10 grams of carbon-14, after 5,728 years, you would only have 5 grams. That is the time that it takes for half of what you originally started with to appear, or for what you originally started with to decay to half of what you had to begin with. So the first issue with this problem is that they don't tell us what we started with or what we ended with. So we're going to select some numbers, and we just need to be sure that they hold the relationship of one number being half the other. So let's say that we started with 12 grams. And understand that I am completely making up a number here, and that's fine. Because if we start with 12 grams, after 5,728 years, how much are we going to have? We will have 6 grams. We will have half of what we started with. So it doesn't really matter what numbers you use as long as you preserve that relationship of that half-life. So I could have just as easily said I'm going to start with 20 grams and then I would have 10 after the half-life has expired. Or I could have said I'm going to start with 100 grams and I would have 50 after the half-life had expired. So you just want to be sure that the numbers you select preserve that half-life relationship. Okay, so if we've got these numbers, if we're starting with 12 grams, that is our A sub 0. Remember, that is your initial value. And so the A is going to stand for amount. So the A sub 0 is your initial amount. And after the half-life has expired, this is your amount. All right, so this will be the A sub T, or the A sub 5,728 years. All right, and our job is to find the A. So again, we're looking for this constant A in the formula. So let's plug in and see what we've got here. So I know that the A sub T is going to be 6. The A sub 0 is going to be 12. The little a is what we're looking for. And the time is going to be 5,728 years. Now, how do we solve this equation for A? We're going to first isolate the exponential. So we're going to divide both sides by 12, which is going to give me 6 over 12 is 1/2, is equal to A raised to the 5728. Now, once that exponential is isolated, our next job is to write it with the same base. But because one of the bases is a letter, a variable, that's going to be almost impossible to do. So we're going to have to figure out another way to do it, and we're going to have to rely pretty heavily on our calculator. So what we're going to do is we're going to try to, since this is raised to the power of 5728, we're going to take that particular root. So I'm going to take the 5,728th root of that, which will cause it to cancel out, and I'm going to do that on both sides. Okay, so let me back up just a second and be sure you understand. That's no different than me saying if I have an A squared, how do I get to an A? You would take the square root. Okay, it's just that our numbers are larger here. All right, so when we do that, this part on the right is just going to become an A. And the part on the left, we're going to need to put in our calculator. Now, the easiest way to put that in your calculator is to put it in as an exponent. So if you'll put it in as 1/2 raised to the 1 over 5728 power. And again, remember that that can be done because, again, remember if you've got a square root, that's the same thing as a 1/2 power. It's 1 over whatever your root is. So entering that in our calculator, 1/2, and be sure you put the 1/2 in a set of parentheses, and raise it to the 1 over 5,728th power, we'll end up with an A value of, and it's a pretty lengthy decimal, 0.999879. All right, so now we can take our function, which looks like A sub t equals A sub 0, and we're going to plug in the A that we have just found, so 999,879, and raise that to the t power. All right, and so now we have our function that we can work with if we were asked to identify values for carbon-14. Another application for exponential growth or decay is that of compound interest. So let's look at one example of that. First, a definition and a formula. The compound interest formula: an investment of P dollars compounded N times per year at an annual interest rate of R has a value after T years of, and the formula is A sub N is equal to P times 1 plus R over N raised to the NT. And so let's look at an example. Sandy invests $10,000 in a savings account, earning 4.5% annual interest compounded quarterly. What is the value of her investment after 3.5 years? So I'm going to begin by just jotting my formula down from the previous slide so we can work with this formula. And let's plug in the values that we know. So we know that she invests $10,000 in a savings account. So the $10,000 is the principal, and that's going to go in for the P. The interest rate is 4.5%, and so we would want to put that in as a decimal. And so remember that you're going to move the decimal 2 places to the left. So 0.045 over n, and n is the number of times the interest compounds a year. So we're told that interest compounds quarterly. So how many quarters are there in a year? There are 4. So n is going to be 4. And our time is 3.5 years. So we'll put in 3.5. Now, in terms of working this out, we do want to go to our calculator with it, but you may find that you want to do some of the calculations separately. For example, the 4 times 3.5 is going to be 14. So that could easily be done. You may also want to calculate this part inside the parentheses separately, typing in your calculator 1 plus 0.045 over 4. That would give you 1.01125. And if you're doing that, just please be careful with your rounding. You want to carry that decimal as many places as possible. And then typing the remainder of the problem in your calculator, you will end up with a final answer of $11,695.52. Let's try another one. 9 months after depositing $520 in a monthly compounded savings account, Frank checks his balance and finds the account has $528.84. Being the forgetful type, he can't remember what the annual interest rate for the account is, but sees that his bank is advertising a rate of 2.5% for new accounts. Should he close out his existing account and open a new one? So he can't remember the interest rate. Our job is going to be able to figure out what that interest rate is. So again, let's take our formula. And let's plug in what we know. So his initial deposit is the P. So 9 months after he deposited $520. So I know right now that I can put the 520 in for the P. The savings account compounds monthly. So remember that that is the N value. And so how many months are there in a year? There are 12. And so we'll plug a 12 in for the N. He finds the account has a balance of $528.84. So that is the final amount in the account. So that'll go in for the A. Being the forgetful type, he can't remember what the annual interest rate is, so that means we're looking for the R. And we want to find out if his interest rate is more or less than the 2.5 that is being advertised for new accounts. For our time, we're told that the time is 9 months. So 9 months, remember that your T needs to be in terms of years. So 9 months is 9 out of 12, because there are 12 months in a year, which is 0.75. So we can plug a 0.75 in for the T. And now our job becomes to solve for the R. So again, let's do what simplifying we can do fairly easily. So one thing that I can do is I can multiply the 12 times the 0.75, and that's going to give me 9. All right, so I'm going to go ahead and just sort of mark through this and say to myself, okay, that's equal to 9. We know that in order to solve, we have to isolate the exponential, which means that we are isolating the parenthesis raised to the power. So let's go ahead and divide by 520 on both sides. So that's going to clear those two out. 528.84 divided by 520 is 1.017. So we are at 1.017 is equal to 1 plus r over 12 raised to the 9th power. Now, how do we get rid of that 9th power? Remember that if we have something raised to a certain power, we can take that particular root. So we can come in and take the 9th root of both sides. Remember that taking the 9th root would be the same thing as raising to the 1/9 power. So I'm going to take 1.017 and raise it to the 1/9 power. And I'm going to get 1.001874768 is equal to 1 plus r over 12. Okay, what do we do next? We're solving for r, so we can subtract the 1 from both sides. And let me erase some of this over here so we have some room to work. Okay, so subtracting the 1 from both sides is going to give me 0.001874768 is equal to r over 12. Then the last thing I need to do is multiply both sides by 12 to clear that fraction. And so we're going to multiply that times 12, and that should give us our answer of 0.022497 is equal to r. And so as a percentage, that is roughly 2.25%. And so that's what he's currently getting on his account. The new account would get 2.5%. So he would have a slight advantage if he switched to a new account. The last thing that we're going to look at is compound interest with the number e. So the number e is kind of like a pie in that it stands for a particular number. E is equal to 2.718 and so forth. We will see this come into play when we talk about compounded interest that is continuously compounded. So not compounded monthly, not compounded quarterly, but compounded continuously. And our formula for that, compounded continuously, is that the final amount, A of t, is equal to P, which is your principal, times E raised to the R times T. And R is the interest rate and T is the number of years. So let's look at an example there. All right, so if Sandy has the option of investing her $10,000 in a compounded continuously account earning 4.5% annual interest, what will the value of her account be in 3.5 years? So her initial investment is $10,000. We're going to put that in for the P. We know the interest rate is 4.5, so we're going to put in 0.045. And we know that the time is 3.5, so we'll put in 3.5. And so we'll enter that into our calculator. Right, again, if you want to do the 0.045 times the 3.5 separately, you can do that. So that's going to give you 10,000 e to the 0.1575. And then you can type the rest of it in your calculator. Now you should have an option on your calculator, depending on your calculator, to use at the E. And so you may need to take a minute and find that on your calculator, but it should type in exactly like what we have here, 10,000 e raised to the 0.1575 power. And that's going to give you a final answer of $11,705.81.